In the previous video, we actually evaluated a dumb and newly born convolutional neural network, and we saw that the performance was absolutely disastrous. In this video, we're going to be training that neural network and see the effect. Hello everyone and welcome to ML Done. So let's just remind ourselves of what we've been talking about so far. So we have blah blah blah. So we have this dataset class, right? So nothing new here, just reminding ourselves, okay, we're loading the dataset, like healthy and tumor brain MRI images. We are creating our NumPy arrays of the actual images and the corresponding labels. We're considering ones for the tumor label and zeros for the healthy label. So in other words, positive cases and negative cases. This is our the len function, so this is where we are actually overriding the dunder function, and here we are actually returning a dictionary of the actual images and labels that live in this particular index, right? And here are the keys of that dictionary. So nothing new here, and this is a little function that we've written here for normalization. This is our convolutional neural network. We've seen beautifully how these numbers turned into, like the initial numbers turned into 256, and we've computed all of that. So we have hopefully gotten comfortable with our model so far, okay? So in the previous video, let me just show you what happens. So we create an object of the class, and there is a class, and we normalize all the data within. We create a device, which is our CUDA or our GPU, and we put our model on top of, so we're actually creating a model, and then we put it right on the GPU. And then we create a data loader, right? So if I just print this, so here model.eval, we said that this does not turn off computing the gradients, right? Remember, we talked about this in a very detailed manner in one of our previous videos, right? So here, this is the outputs and the actual ground truth. So this is the bit where we're turning off computation of the gradients. And so in our data loader, every D that is retrieved, remember, is the same dictionary that I showed you in the get item bit of the data set, right? So we get the image and label key values, and so this is the outcome of that is the actual image values, and the outcome of this is the corresponding label. We put both of them on the GPU, and then using this command we run the entire image through our convolutional neural network. So this is the prediction of the model, and here we're just saving the outputs or the y-hats and the actual labels, right, in our two lists that we have defined here. And you remember that this bit over here is how you convert a CUDA torch, a CUDA tensor all the way to a NumPy array, right? So let me just show you how this works again. So just as a warm-up, and here we are actually concatenating all the outputs and the labels, and this is the threshold function that we use to use the threshold value of 0.5 to sort of, threshold and cut off the raw output values of your y-hats. Remember, it's a sigmoid unit, right? It outputs values between 0 and 1, right? So we define the threshold function, and using the accuracy score functionality that we have defined, we are passing the actual labels and the thresholded output values, right? And we saw that, okay, it's not that good. It's like 62%, and this is the code where we actually used to visualize our confusion matrix. I can't talk today. And the confusion matrix, so in this case, basically the model is predicting everything to be tumorous, right? Everything is, so everybody has tumor. As far as the model is concerned, nobody is healthy. So that's not good, right? And it sort of jives well with, with the poor performance at a 62%. And one more thing that I did that I think I didn't do the previous time was that I actually visualized these raw outputs. Just so we have an idea in terms of what is my model actually generating, right? It would be interesting to see that, right? So I'm just creating a figure, and the outputs, I'm just plotting them. And remember, I am actually dividing the portion of the outputs that belong to when the input of the data belongs to the tumorous class, and also when the inputs of the network belongs to the healthy class, right? So that you could see how does the input of the network change corresponding to the type of image that was inputted into the model, right? And then we put a grid on top of that. So if you look at this mess, so remember the output, this y-axis is your output, right? And it is a sigmoid function, so obviously it cannot go beyond 1 and 0. And so you notice that it's just a noise. So the entire output values for all of the data in your data set of a dumb model is just a bloody noise. There's nothing informative about it. And this red line over here is what I was talking to you about. So all the outputs that belong that have appeared on the left hand side of this network belong to the positive class. So basically the output of the network when the inputs belong to the tumor class. And everything on the right hand side is the output of the network when everything belongs to the healthy class. I think that's the way, not the other way around. Hopefully I'm not wrong about this, but I think that's the case. 'Cause as you see, it's fully noisy, so it's really difficult to see what the network is trying to do here. But don't worry, we're going to get around this. Now, let's train this dumb model. So this is what I've been advertising for the past God knows how long. So in order to train a model, let me just create a bunch of cells. So what do I need to train a model in Pytorch? So you need the learning rate, you need to define an optimizer, you need your data loader, and then here is where you're going to be using model.train rather than model.eval. And model.train is there because if you have dropout or batch norm, you want them to behave in train mode, right? This is what we talked about in absolute detail in previous videos. So let's just go ahead and define all of these values. So eta, learning rate, let's just define it as 0001. Right, and the optimizer. Now, one thing about the optimizer, what is an optimizer? The optimizer dictates how you walk on the error surface with the hopes of finding the global minimum or a very good local minimum, right? So when you compute the gradients during your back propagation, what happens actually, you compute the gradient and then the question is, how the hell am I going to incorporate this gradient with the values of my weights to update them? That method of integration, whether you're going to be using momentum, for example, or not, and the whole idea of adaptive learning rates, like how to adapt the learning rate as you walk on this vast terrain that is your error surface, the way you adapt your learning rate, all of these things are dictated by the type of optimizer that you use. And the very well-known optimizer is Adam. It is an optimization technique that uses momentum and it has this adaptability of the learning rate capability within. And lucky enough, you don't need to code this from scratch. So Pytorch already comes with with all of the optimizers that you basically might need. I'm not sure whether they have Nestrov, to be honest, but well, the one and only optimizer that everybody is like the solution to everything is, you see, we have all these optimizers here, is Adam. Right? So whenever you didn't know what optimizer to use, go for Adam. It's all over the place. And for the good reason, really. So what do you need to pass to your model or to your optimizer? It's all the parameters of your model, all the learnable parameters of your model. So you're basically telling the optimizer, look, I want you to optimize these parameters, right? And so those are all the ways in your convolutional layers or fully connected layers, right? And the way to do that, you've already defined your model. So you just go model.parameters, right? And the second bit that is required is the initial learning rate for your optimizer. Remember, Adam is a learning rate adapter type of an optimizer. So it just waits for your initial value for the initial learning rate. Then it's going to keep changing it depending on the steepness of your the error surface on which you're walking around, right? So the initial learning rate is my eta that I've already defined, right? Now, next thing, we're going to define our data loader. So let's say I'm going to be, training on the entire data set, right? So the purpose is to just show you what training actually looks like. And again, the defining data loader is very similar to what we've seen before. Again, using the data loader object, you pass your dataset object, you define your batch size, and here for training, it makes to keep the shuffle true, right? So for every epoch of your training, you keep shuffling the data and you pass the newly shuffled data into your neural network and you update the weights, right? That's just how the training of an artificial neural network works. And let's just say I also define the number of epochs as, let's say 400 maybe, yeah? I'm just coming up with these values. Next, we have already defined the model, right? So I'm gonna putting model in train mode, right? So batch norm and dropout are gonna be behaving in train mode. We don't have either of them, but this is just good practice. Always get into the habit of saying model.train when you want to train a model and model.eval when you want to test or basically evaluate the model. Get into that habit. That's very useful. Now, finally, so let me just run this. Okay, great, it's working. So model.train also returns a list of the elements of your model, which is fine. Next thing, we're gonna start a loop for our epochs, right? So I'm gonna create a loop and it's gonna be range from 1 to all the epochs, right? So it's like 1, like in this case it's 400. So for every epoch, what I want to do, I want to compute the errors across the entire epoch, okay? So because of that, I will define a losses list. So this is to keep track of all the errors within that epoch, and then it resets at the beginning of the next epoch, right? There's a reason why I'm doing this, because I want to take an average, for example, of the losses across a given epoch, print it out, and then reset and go and start recording the losses for the next epoch, right? So by loss, I mean you make a prediction and you screw up or you do it well. So that loss is computed using an error function. Now, in an epoch, I'm going to go through all of the data points that I want to use for training. Now, we have defined this beautiful data loader, right? This data loader, right? So I'm going to be using the data loader, and again, I'm going to define another loop for D in the data loader. Now, the good thing about it is, every time the data loader wants to retrieve something from my dataset object that I've defined here, the dunder function getItem is going to be called, right? So this is not new. We've seen this idea before. So that part is okay. Now, here's the tricky part. Maybe I'll show you this one later. So, okay, I'm going to skip a line. I'm gonna write it at the very end. I want to show you the importance of having it. So for now, let's say, so we are again no stranger to this bit, right? We've seen how it works. We grab the data and the label, we put them on our GPU, and here we predict the actual output of the model. So this is again the same as before. Now, the bit that is going to be changing is where we actually compute the error, right? But before I do that, I just want to make sure we are clear about one particular thing. I just want to make sure that the shape of my ground truth and the shape of my prediction, like the shape of these tensors, match, because that's important. So because of that, before I continue with writing up my code, this is good practice, okay? These are little bits of painful lessons that I've learned over the years. So try to get into the habit of these little checks. This will make your troubleshooting much easier. So let's take a look at the shape of the prediction tensor and the actual ground truth tensor. So I'm just gonna call sys.exit, means that like terminate the execution. So if I did that, What's the problem? So for epoch in range, sorry. Okay, look. So the shape of my prediction is 32 by 1, whereas the shape of my labels are just 32. And 32 is because of my batch size, right? My batch size is 32. So what this means is I just need to just get rid of that extra dimension in my y-hat. These things happen, right? So the way to do that is using the squeeze function. So if I were to actually do that, like squeeze, I can't spell today, right? If I were to do that and print it as, okay, you see, both are 32. So if I want to compute my error, and I want to pass my prediction and my ground truth to the error function, in this case a binary cross entropy error function, I'm going to be making sure that the dimensionalities match. So because of that, I'm going to be squeezing my y-hat. So let me just get rid of this bit. So let's define loss function. So this is a binary classifier case, right? A binary classification. In binary classification, as I'm sure you know, you use a binary cross entropy error function. And again, you don't need to worry about defining your own error function. Again, Pytorch gives you everything you need. So you're fine. So the error is, so from the neural network package, and then that BCE loss. So you define a loss object or an error object, right? And then you pass your ground truth and your y-hat to it, right? So it's going to be error, y-hat, and the label. And remember, I said the dimensionalities don't match, right? So I said that I'm going to have to squeeze this just to make sure the dimensionality of both of them is 32. So this is our error, right? So you got 32 values in the prediction, 32 values in the labels. Now, you need to merge these together. Like 32 values of our error, merge it together. Usually what they do, they just sum them together. A method of aggregation across all of this data points in your mini batch. So again, you can call torch.sum of the entire error vector. I think we're okay here. So let's call this loss. And okay, here's a bit. Here's the important part. You have computed the loss. This is the forward pass of your neural network, right? Now what about the backward pass, where you compute the gradients in your computational graph? Very simple. It's ridiculous how simple it is. You grab your loss, you call backward. I think I'm spelling it wrong, right? Backward. Yeah, it's actually okay. This bit computes backpropagation. So backpropagation starts here. And after you compute the backpropagation, and you do the backpropagation and compute the gradients, you need to use those gradients by the rules dictated by your optimizer to update the parameters of your model. So the next step is to actually update the parameters of your model, hence learning. So the optimizer, we have already defined it. We call it the dot step functionality of the optimizer. It means that, okay, we've got the gradients, take a step, update everything. All the parameters, the learnable parameters, right? Now, I mentioned that there is a line that I'm gonna skip now. Always, always, always make sure that you will call the reset. So you reset your optimizer so that it will not cache anything. So it's always good practice to call the zero grad functionality of your optimizer at the beginning of every epoch. It's very, very important. So it is very important to call the zero grad functionality of your optimizer to make sure it doesn't cache anything at the beginning of feeding every data point into your model, right? So this always make sure you have it there, right? So before you feed the next data point, you make sure that you are zeroing all the grads, and then you do the rest. You compute, you get your data, you label, you compute the prediction of the model, you compute the error. and you compute the gradients, and then you take a step and update the parameters. Now, one more thing is that we're gonna be keeping track of all of these losses, right? So I'm gonna be saying losses.append, and this is where I keep my loss. So loss is a tensor, right? So in order to get the value of loss, that one value of loss that I'm interested in, I'm gonna make sure that I will get the item. So the item command actually grabs the value of a tensor, right? I think I've got it right. Yeah. So this keeps track of each individual error value across for every data point, right? So at the end of going all the way through all the data points in my data set for the first epoch, I will have saved all the data points in my losses list, right? And after that is done, and after the first epoch is done, I'm just going to be printing out my losses. And you know, the way I'm going to be printing it out is going to be, say, every 10 epochs, right? No point on printing out for every one epoch of 400 epochs that I have, right? So just written out this code before, just to avoid wasting time, that I'm just copying it here. So when the epoch plus 1 divided by 10, the remainder of it is 0, meaning that if epoch is 9, 9 plus 1 is 10, so the remainder becomes 0. If epoch is 19, 19 plus 1 becomes 20, so 20 divided by 10, the remainder is 0. So every 10 epoch, we are printing the error, the number of epoch. What epoch am I in at the moment, and what is the loss at the moment for that epoch? Remember, when you finish all the data points in your mini batch, and you get out of this first loop, your losses has all the individual errors across your entire data set, right? So in that case, if you want to print out some aggregated value of all of those losses, you can just take an average of those losses, right? So that's what I'm doing here. And when you go to the next epoch, right, again, you are resetting your losses. This is just how I'm doing it. You don't have to do it this way, really. So this is the training cycle. So let me just train it. Okay, good. So this is just happening. And as you notice, we are printing every 10 epochs, right? And as you notice, the error is already going down. It keeps going down and down and down. It means that the training process is actually working, right? So as this is happening, I'm just going to be taking a sip of my coffee, and I think I'll be back with you in a second. Right, welcome back. So the training has stopped, as you can see. We have 400 epochs, that's the last bit, and this is the final loss that we get. So we went all the way from 0.62 all the way to 007. Now, let's see the same properties that we had, the same visualizations that we had observed before, the same confusion matrix that we saw before, the accuracy score that we had computed before. Let's see how all of those things play out now. Evaluate a smart model. Maybe smarter model. So how do we evaluate? Again, I'm going to be using the exact same code that you've seen before, right? The way we evaluated our dumb model before. So in order to avoid any wasting any time, I'm just going to print it. So model.eval is called. We're passing the entire data set again. So we're basically evaluating on the same data that the model has been trained on, right? Nobody does this, right? This is just to show you what training looks like. I will show you how to define a validation set and separate the training from validation set. I'll show you all of that. But I just want to show you the effect of, okay, the simplest way possible. Have I learned the data points that I've been trained with? Have I learned the hidden patterns or not? That's what I want to show you. So I've saved all of the outputs and the ground truths. So we've seen this accuracy function that we've written before. So if I pass, this is the threshold function, right? We've seen this before in the previous video. Look at that. Accuracy is 100%. What was it before? Before it was 62%. Holy, wow. So that's great, right? Next, let's print out our confusion matrix. So again, I'm gonna copying the same thing, right? The same commands for printing out the confusion matrix. Let me just make sure that I'm just being lazy, right? I mean, I could have just put all of this in a function, but that's not the point. So I'm just going to be printing out the confusion matrix of the labels and the thresholded outputs, right? Look at that. So here, of all the 154 healthy images, all of them have been predicted as healthy, and of all the Of all the 91 predicted, 91 actual tumor images, all of them have been predicted as tumor, right? So it's doing a great job. Now, the holy glory, the beautiful bit, where I'm actually gonna be plotting the actual raw outputs. You remember previously it was just a bloody mess, right? There was no way to put a threshold around it. And remember, this is the output of my sigmoid, right? And during my training, I'm insisting that I would like the network to learn to produce values as close as possible to 1 for the images that belong to the tumor class, and values as close as possible to 0 for the images that belong to the healthy class, right? And just before I print out, I just want to make sure you're clear with about this. So in my dataset class, where have I dictated those 1s and 0s? Here, right? For tumor labels, I'm going to be insisting that I want you to learn to predict a value close to 1. For healthy, to learn to predict values close to 0. That's where it's happening. Okay, let me see what happens to this mess by just running this chunk. What can I say? What the hell can I say? This is just fantastic. There are things you can see here. First of all, the outputs of your network indeed range from 0 to 1. The network has learned to separate the outputs depending on whether we're dealing with tumor images or healthy images. So all of these outputs belong to the tumor images. You see, they're very close to 1. And all of these outputs belong to healthy images. And you notice that 0.5, which is a line somewhere around here, is a perfect threshold to measure the accuracy. And that is why when I'm actually computing the accuracy and I'm thresholding my outputs, that is why, let me show you the threshold function. That is why I'm using 0.5 as a threshold, because that's the traditional threshold for sigmoid function. And here visually, you see why 0.5 works. You see, it's equidistant from both ends of the extreme of sigmoid. And you notice that with a simple threshold like this, any output that is higher than 0.5 belongs to the tumor class, and any output below 0.5 belongs to the healthy class. Okay, great. So now you know what it means to train an artificial neural network. In the next video, I want to visualize some of those convolutional filters just so you know some sort of, like, visually you know what the network has learned to detect in those healthy and tumor images. The filters, the convolutional filters that the network has learned. I'll see you in the next one.